and we'll talk about advanced testing and what finance can learn from other industries. We are on a constant quest to find better ways of testing software, so it would be interesting to listen what other people think, what other people do, and how other industries exist that are outside of our finance world. We know that there is currently a strong focus on more agile methodologies, but I think today, and I hope today, we will cover not only lightweight methods but more heavier and stronger approaches to achieving better software. So let's start with introductions. Gentlemen, can you please introduce yourself, starting from Milan? Thank you.
Hello everybody. My name is Milan Dvorak. I'm from the company called Netcope Technologies. We are based in Czech Republic. Our main focus is FPGA technology, which is programmable hardware that can offer very high performance. We have two target applications. One is low latency trading. The other is high-speed networks up to 100 gigabits per second, and specifically network security. So it's about capturing all the network traffic, analyzing it all in real time. I'm personally responsible for the low latency trading part. I'm in charge of our solution for low latency electronic trading, both in terms of development and business.
Thank you.
Good afternoon. My name is Rajan Bedi. I'm the CEO of Spacechips Limited. Spacechips is a UK SME, and we design the space electronics which you find on board spacecraft and satellites. The company also offers training courses around the world in space electronics, and that training product has been branded as Courses for Rocket Scientists. Spacechips also offers expert due diligence consulting services for equity fund managers considering investing in the global satellite industry. Thank you.
Good afternoon, everyone. My name is Denis Ignatovich, and I'm a co-founder of a company called Aesthetic Integration. And what we're doing is we're bringing techniques from the area of formal verification, or some people refer to it as formal methods or symbolic artificial intelligence, but techniques that have been used for quite some time in avionics and hardware manufacturing to analyze complex algorithms and really understand what they can or cannot do, and think about the right ways to test that they're implemented correctly. And we're capitalizing on recent breakthroughs in that field to bring these techniques to finance. So focusing on everything from things like fix certification to making sure that the matching engines are implemented correctly to avoid things like bats messing up their own IPO. So these types of things.
Hi, thanks, Dennis. My name is Jim Northey. I'm a Senior Vice President of Strategy and Research at Itiviti. The company was formed of a merger of Orc Software and Cameron Technologies. And my background actually was in aerospace and telecommunications before I sold out to the world of financial technology. Anybody else sell out? Anyway, so it's good to be bringing some of those techniques from the industry into our industry. So, thanks.
Thank you. Thank you very much. So, Milan, is there any difference between what you do to check FPGA used in network security in low latency comparing to ordinary software testing? Do you see any difference in what you do comparing to what people who test websites, back office systems, etc. do?
That's a quite broad question. I guess there would be several differences. because the development flow for software and FPGA is still quite different. Programming FPGAs, is much more low level. It's similar like software a couple of years ago when people still needed to code in C, in low level languages without the abstractions and objects and so on. So that's still the case for FPGA development. That also means the tools and verifications we use are quite different, because the components are typically smaller. The systems are more specialized. So I would say that's one difference. Another difference, I guess, is testing for performance, because with FPGAs you can really make sure your processing is deterministic, like there is no variation in terms of the time you need to do the computation, the processing. In software there are cache misses and interrupts and so on. In FPGA it can be brought down to a couple of nanoseconds, because it's basically real hardware. So there's a much bigger test suites for performance, high throughput, low latency, and so on.
Okay, thank you. And Rajan, can you please tell us about how do you work with FPGAs to be delivered into space, and how do you make sure that they will work according to your expectations in your industry?
When we design electronics for use in outer space, let's say, for example, you take a telecommunications satellite that will live up there 22,000 miles, we will never see it again. So reliability is key for us. And in fact, every microsecond the spacecraft is off, the owner of that spacecraft is losing revenue. So reliability is fundamental for us, and it starts at the component level. So for example, Milan talked about FPGAs. You take a typical commercial grade FPGA that might sell for, let's say, several £100 or dollars. You take a space grade FPGA, that one microchip will cost me possibly $100,000, okay? But when I buy a component at that price, I buy a certain level of reliability. I know that when I switch it on and when I use it in space, it will work, and it will continue to work for 15 years. So when we test, when we design our electronics, we begin at a component level. We use high reliability components. When we design our circuits, for example, those circuits, before we actually build anything, the circuits are simulated to death. They are validated, they are verified, and only when we can sign off through verification will we actually build the hardware. The hardware is then firstly tested at a PCB level, is tested under ambient conditions, is then tested under operational conditions. The complete spacecraft, when all the electronics is integrated, the complete spacecraft will be tested under operational conditions in a thermal vacuum chamber. And only then, when we've gone through those multiple processes of due diligence, can we then say, yes, the spacecraft is ready for launch. But going back to FPGAs, so in the financial world, most people use the latest ultra-deep submicron static RAM-based FPGAs, because those are the highest performing devices. So in the commercial world, 95% of all FPGAs which are sold and used are static RAM devices, because they are the highest performing devices. But in the space industry, 95% of all FPGAs which are used are one-time programmable anti-fuse devices, and these typically lag the performance of the FPGAs that you would use by many generations. So we are a risk-averse industry. Reliability is key to us. However, now, to deliver the next generation of satellite services, operators want to use the latest and greatest static RAM-based FPGAs. So as a result of scaling, intrinsically, that has delivered certain advantages to our industry, but likewise, it has delivered some challenges. So for example, with a static RAM-based FPGA, when used in outer space, the harsh radiation environment can upset the configuration which determines what the FPGA will perform. So when the configuration changes, the consequences could be negligible or they could be catastrophic. And catastrophic means you simply take out a £100 million spacecraft. Okay, so we do lots of testing on the ground. We also go to facilities known as cyclotrons, which allow us to mimic the environment of space, and we can bombard our electronics with radiation. We use other testing techniques such as fault injection. So we use many techniques to ensure that we meet the reliability needs of our customer.
Okay. How would you, Rajan, how would you estimate the percentage of work that goes into more formal methods, so in modeling comparing to more common to finance dynamic verifications of the software?
So typically 60% of our design flow is testing and verification. We might spend, let's say 5 to 10% using formal verification methods to test our hardware and software. And as technology progresses, we use some agile techniques as well.
Okay. And Denis, do you think anything of what is used in avionics might be applicable to finance? Any methods?
I certainly hope so. Otherwise, I've made a very poor career decision. So just to give the context, up until 2 years ago, I was running central risk trading desk at Deutsche Bank, just down the street. And as someone who was effectively FCA approved risk manager, signing off on all code changes for the market making system that I was responsible for, I spent a lot of my time thinking about what the typical question, which is what can possibly go wrong. And anytime there's a headline about Knight Capital or Bats Exchange or Goldman Sachs doing alphabet trading types of things, the obvious answer is there's a lot of things that can go wrong, and you're in this environment where you have to make money, you have to make constant changes to the market making system, introduce new signals, etc. But you're always signing off on these things knowing that if something goes wrong, you're going to get fired the next day. So what we started doing, which was a couple of years ago, is we, myself and my co-founders got a PhD in this area of formal verification. We realized that obviously there is no such thing as a silver bullet that just you press a button and everything, you're effectively de-riskified against all external factors. But for a decent amount of things that finance has to deal with, such as understanding all the different edge cases of let's say, a matching engine, or understanding all the edge cases of connecting to an exchange, things like this, there are quite a few techniques from other industries that we can actually leverage, and that's what we're doing. So there's a lot of talk about CPU or hardware verification, things like this. I just want to give you kind of two examples of how other industries have switched using more mathematical, more rigorous methods. So about 20 years ago, you might have heard about Intel and the debacle that they had with their floating point operator. So they had a glitch in the design of their microchip. And as a result of this glitch, they had to recall their Pentiums that they sold or manufactured, costing about $500 million. This is, from money from 20 years ago, so a lot more now. and their competitor, AMD, was coming onto the scene with a compatible processor, K5. And what they realized is that if they had a similar issue, it would just blow them out of the water because they're just a much smaller company. So what they did 20 years ago, which was revolutionary for the industry at the time, but is now a standard in hardware manufacturing, is they create a mathematical model of the algorithm, effectively, which is encoded as CPU as hardware. And they try to mathematically verify that the same issue would not hit them, something that happened to kind of Intel. And in the course of that, they discovered bugs, they fixed them, went into manufacturing, did not exhibit anything like this, and ever since then, it is a standard of how things are done in hardware manufacturing. You simply cannot analyze a modern microchip with billions of different parts on it without using automated techniques to reason about infinitely many possibilities. So another kind of closer to home example of radical changes that are brought on by these formal methods is, you might have heard about debacle, which was Windows Vista. So a lot of banks, a lot of financial institutions never adopted it because it was just so buggy. And what Microsoft realized is that most of the issues that its clients saw when they were using Windows Vista had nothing to do with Microsoft. In fact, most of the bugs were in the what are called device drivers. So it's effectively vendors that had to write code that interacted with Windows Vista that had bugs in them. And what they did, again, which was fairly new for the industry, is they used their internal formal methods tool, actually something called Z3 that Jim was very well aware of and used in the past, but they forced everyone that was writing device drivers for Windows, for Windows 8, the next version, to actually submit their source code to a formal methods tool that automatically checked the logic to make sure it never goes into this hourglass scenario that I'm sure all of you have seen before. And because of that, they had this radical improvement in performance from Windows Vista to the next version of Windows. And now, for you to be Microsoft certified vendor, you have to submit to this process. And what's special about that industry is over the past, I would say 3 to 4 years, there have been breakthroughs in mathematics that allow us to take those techniques and apply them not to Boolean logic, which is how hardware operates, but really think about fixed messages and nonlinear derivatives risk, and to really think about modern day trading systems and matching engines with the same type of rigor. So I would argue that there's quite a lot of few things that we can take from industries. And again, it's not a silver bullet, but a lot of things that people do right now manually or using random number generators can be automated with unprecedented rigor and go a long way to making sure that we're spending a lot less time on trying to show that we're compliant by effectively automating these processes.
Sure. Sure. But formal verification requires substantially more effort than writing the software code itself. So do you consider it applicable across every part of financial industry, or it should be focused only on more riskier part of the systems that we deal in finance?
So the answer is it is not applicable across all of finance. So for example, a lot of people in finance are writing desktop applications that are showing you stock price charts and things like this. So this is not a technology for this. But just to give you an example of something that we're doing for a top-tier American investment bank right now is we've taken a fixed specification of their dark pool, which is this chunky 150-page PDF, and we've converted it. We spent maybe 6 hours on just taking that information and converting it into this language, which is very similar to something that the industry is pushing for, which is called fixed orchestra. But that type of a format, which is machine readable and is mathematically precise. So you take that 150-page PDF, spend a day, convert it into this format, press a button, and you get all of these different edge cases that one must consider when they're actually connecting to this venue with a push button. You spend a day doing that, and then you have weeks worth of savings from what you would have spent actually trying to figure out how that thing works. Number one. Number two, next time you have to make a change to that specification, you spend 2 hours, you press a button, and it shows you all of these edge cases. And then when your clients have to connect to it, instead of them trying to figure out what does all of these things mean, they actually have tools that allow them to ask questions, that allow them to automatically create simulation environments, get compliance reports, all of these things. So there is an upfront cost, I agree to that, but I would argue that this is the type of cost that people would want to spend, because it'll give them at least a 10x performance improvement.
Okay, thank you. Jim, so in your strategic research, are there any particular industries, any particular ideas that you take into Itiviti and try to implement in real life?
Yeah. Well, Iosif, it might surprise you that I have some thoughts about this area. Yeah. So I'd like to start off, just want to reiterate, the first place I want to start was model-based testing. What's amazing to me is if you think about formal methods, you think about the UK. I mean, really, formal methods sort of lived and were founded here in the UK. All the conferences are here, and I'm surprised we're not using it in more areas. There was a book written. Everybody looks pretty young here, so this is my 39th year doing this stuff professionally. And of course, the bad thing about working in any industry for 39 years, especially finance, if you haven't made your money by the time you're 50, you're considered a complete failure. But anyway, I don't know. I seem pretty happy, so maybe that's a measure of success. Huh? Anyway, James Martin wrote a book in the late 1980s called Designing Systems from Provably Correct Constructs, and it really it detailed what was done on the space shuttle for the landing and takeoff systems and how they designed systems. And I thought at that time it would start a revolution in terms of software industry, and it never really materialized. I mean, we still have, in general, a lack of rigor. And but I think that book really did get people starting to think different. And for me, it sort of veered my career off into learning things like Z and other languages. And then when I briefly retired and went to the university to teach, I got to teach the formal methods classes because no other faculty member wanted to teach them. But I think it showed that you can approach software differently. And so when we built the SIBO matching engine in 1999, I brought in a group of consultants, Bob Binder, who's now with the Software Engineering Institute, and we attempted to use model-based testing. And at the time, the limitations were really more in the tools. They used a language called Prolog. Does anybody remember Prolog? And it really didn't have the performance and capacity to generate the cases. A few years later, Microsoft, as part of the consent decree with the Justice Department, had to validate 3,000 APIs to say, does your specification documents match your software? And so Microsoft actually built a tool. It's still available, I think, only in Studio 10. Alas, they're no longer keeping it current. It was called Spec Explorer. And it actually sat on top of Z3, which is a third improver language that Grant Passmore and other people worked on it at Microsoft Research. And they actually used that tool to generate all the test cases. And so recently, about 3 years ago, I developed a RESTful API for one of the big top 3 market data vendors to remain nameless. And we actually employed Spec Explorer on the respect. And what was amazing to me was from the spec itself, which you can actually codify fairly well RESTful API, we generated over 45,000 test cases instantly. So, a little specification up front to be able to generate 45,000 cases and all the various edge cases. There's no way a human being can come up and determine what all the edge cases are. So what do you see in normal systems failure that's not a hardware or some other outage? And I'll get into that more in a minute. What you see there is rigorous and incomplete development at work. And people say, oh, well, who would have ever thought that case would have happened? Or, you know, it's amazing that that glitch got there, you know, and everyone's actually surprised, like, you shouldn't expect these things to happen, when in reality, they're actually very predictable. So model-based testing is one that I really believe in, because I've seen it with my own eyes and actually seen it work. Then I wanted to switch to a couple other topics really quick as a laundry list, and I think I'll put together some notes and put them up on the web later. But another area that I think is important for people to start adopting is, how many have heard of chaos engineering? Chaos engineering was developed in Netflix and other places. And in general, when I go into any of our shops, including my own sometimes, don't record that. You know, most people are afraid of their systems. They're actually scared to death. You know, you have to say, don't touch anything, it's working. You know, chaos engineering takes a whole different perspective on that. And, you know, it's working, break it. And furthermore, be willing to break it in production, you know. And so, you know, I think some of the keys in chaos engineering that Netflix does is, one, you know, vary the real world inputs, run experiments in production. Don't be afraid. Don't be, and the whole goal of chaos engineering is so you can get control and manage your system. It really is a behavioral modification technique for systems management and operation. You know, it really addresses the psychology part. The other parts are automate your experiments and run them continuously in a production environment. And then, but there is a caveat here, and I love the terminology, because it goes back to, remember one of the previous panels today we talked about nuclear reactions, and be sure part of the chaos engineering is engineering work. When you're injecting your faults, make sure you minimize your blast radius. So if things fall apart, you know, you don't want to make, you know, I mean, I just imagine the thoughts of like Oppenheimer and those guys, you know, when they think, there were certain mathematical equations that said, once we cause this chain reaction to happen in controller, it'll literally continue on throughout the entire atmosphere and destroy the entire planet. Right? I mean, that's what, so, you know, you have to focus on your blast radius. But, so chaos engineering, I hope that's something you guys will take away with. And basically, it's saying, be brave enough to operate on your system and actually make sure it's testing. And then another couple things, real tough in our business. We used to be able to do it. Even 10 years ago, we walked into, there was a company called Archipelago. How many remember Archipelago? And we walked in with a system. This is Rolf Anderson and I. Rolf Anderson and Panther's now all part of Goldman Sachs. But and we were able to compress and run their entire busiest day, okay, in 3 hours. You know, we were able to show them this running on and so there was something we used to do in aerospace for gas turbine engines, where we would run advanced mission testing. You know, we would like to go through to run the whole life cycle of a typical aircraft, and we'd like to run it through that engine and just maybe and try to reduce that by a number of years in terms of the life cycle. The last thing that I would like to bring in is something that we seem to have lost, and they do this a lot on electronic circuitry and semiconductors even today, and that's design for test. Design the system for test. If you look at automobiles now, you have this little interface, you know, it's you plug in and you can actually read values and run diagnostics. So design for test. And the best book, I think, in that gives that pattern is there's a book called Software Architecture and Practice. That's a good book for us to go back and read. All this agile method and all this other stuff, it's just turned us all into hackers, very informal developers. And if you go back and you actually take a look at that book, you can see there are patterns out there for designing your system for test. And our systems are as complex as anything else on the planet now. And so designing for testability, I think, are key things that we sort of lost in this haste to develop all this complexity. So I think that's sort of a summary of the things I think that I've learned that we could bring to the industry. I think one other interesting point was I did a lot of work on fault-tolerant Unix systems after my little brief stint at AT&T Bell Labs. And I was helping Rockwell Collins with a railroad control system in the very early 90s. And naively, I walked in there and I said, oh, under that scenario, you stop the train. And literally the whole room stopped. A couple of people let out of gas. And they had changed culturally, and I think there's something important to this. This goes into more of the sociology or the group psychology of this was, you have to watch what are your biases and your assumptions that you're making about your system, because those assumptions can ultimately do you in. And so everyone was trained on that team at Rockwell is that you never ever stop a train, because if you get into a failure mode where you have to stop the train, it's too late. Because trains don't stop. When you think of it, when a train stops, if you have to stop a train, it'll stop in 2 miles. And so and I think that thinking is also important part. What are the assumptions that your team are carrying around? Because some of those assumptions are what's going to end up causing a system outage. So some thoughts from other industries. So thanks.
Cool. Thank you very much. So we do have a unique set of speakers. So are there any questions from the audience about using advanced method? No? Okay, cool. I do like very much the idea about chaos, and I do think that if you have a production system and there are no defects, that it is not really a stable system, it is rather a rigid system. So when you do have lots of defects, it makes known defects. It makes the system more anti-fragile, and especially during development phases, if defects flow from one stage into another, they pass additional knowledge with them, and overall it makes the system substantially more stable on a micro level. Okay, but still, should we operate in market infrastructures, other financial organizations look more towards more agile approaches or towards more formal? So do you have any view on that?
I don't think those two are mutually exclusive things. When again, it's kind of like what Jim referred to as model-based testing, and this relates to formal verification, things like this. These are techniques that can, do things that typical human beings are just not. Well, human beings are not wired to do. So this is kind of like it's that question is translated into something like, should we use accountants or should they use calculators? So we should use accountants that use calculators. And so we should do agile types of testing, but anytime we have a complex model or an algorithm, let's employ automated tools that allow us to understand all the different sequences of events or possible outcomes. So it's I guess my answer to that is let's do both.
Yeah, and I think what you want to do is at some point formalize the output or the system that's developed in an agile manner. I mean, agile really talks about iterative, repeatable development and constant interaction with the user as you're sort of discovering what a system's supposed to do. What agile was never intended to do, and I'm trying to remember, first name was Scott, the other guy, there was a guy who really was sort of broke from the agile community and there's agile modeling and agile database design. And most of the problems I see with agile development now in our industry is when you move away from really some set pattern of an architecture, things get very messy and very complicated because people are just cranking code. And it's amazing how fast you can rewrite code and get into a refactoring mess with the modern tools available. So I think you need to have architecture work, but it needs to be part of that. And at some point you have to formalize it. If you have a matching engine or you have an algorithm or you have some sophisticated smart order router behavior, these things at some point need to be understood, and there are tools that you can model them and then actually test them under using model-based testing approach to generate the test cases that go in. And if you don't have enough information to where you can specify, say, what your matching engine's doing for a dark pool or for a venue, or if you have a smart order router you can't do it, then you're really not behaving in a professional, ethical manner in terms of your clients and in terms of your investors and stakeholders, I think. So I don't see them, as Denis said, I don't think these things are mutually exclusive. I think they have to be used together. So
that's actually, I think you brought up a great point. Is a lot of when we speak to clients and when you come in, you say, listen, you have, let's say in a typical bank that runs a dark pool, let's say we have 3 broad categories of stakeholders involved. You have compliance, you have let's say business/product managers, and then you have developers, and then you go in and say, listen, okay, your compliance has one idea of what it is that this thing does. Developers have a different idea, and then product managers and etc. they have a different view. So you have a lot of this information that is very subjective, and documentation quite often is ages old, and most likely the person that wrote that thing is no longer with the company. So you have a lot of these ideas as to what things are supposed to operate like, what it actually operates as, and the exercise that Jim just was discussing is that you have to be able to go precisely specify what it is it's supposed to do. So it's something that people naturally don't like doing. It's in the same way that high schoolers have to be forced to do homework, right? Why would I have to go and take this PDF that was written in ambiguous English prose, or this documentation, or these test cases that someone wrote, and actually precisely specify what it is the thing is supposed to do in a way that I can explain to regulators, I can use to generate test cases, I can run against historical data to make sure my audit is correct, etc. So if you do that, then a lot of this noise is in the system. So if you think about, what's the ultimate goal? Finance spends about $240 billion a year on technology and compliance. Only 25% of that goes towards new technology development. Why? Because of all of this noise. Because at the end of the day, it's very difficult for people to sit down and spec out in a mathematically precise way how the thing is supposed to operate. Right? You have 5 people involved, you'll have 7 opinions as to what it is that it's actually doing. Right? So that's the exercise. That's doing things in a more rigorous, mathematically rigorous way, is forcing people to have certain discipline about doing things. And once you get to that state, yes, the initial kind of response is, no, I don't want to do it, all of these things. But once you get there, you're much more disciplined. You have this great payout in terms of automation, etc. And it allows you to spend your budget on doing things that are adding value and not adding noise to the system.
But say, going back to method 2, when regulators specify standards, I think they are, in some cases, intentionally vague. So you are not specifying that these are precise KPIs or technical tests that you should follow, but they rather define principles that are considered to be prudent from human perspective rather from technical point of view.
Absolutely, but I think if just in method 2, so I forgot the exact clause of all the regulations, but there is, for example, one of the things that is clear there is your design process has to be delineated from your development process. So if you have a model of what it is you're trying to build, and you can actually use it to test for production environment, that's definition of delineating your design from development process and from compliance, let's say. So they're saying these things in a convoluted way because they, there is this gap, because if you think about the way that avionics is regulated, people have much more rigorous standards. Hardware the same way. Now, it's actually funny. The Department of Transportation in the United States has, a couple of years ago, commissioned a study on how to use formal verification to make sure that self-driving cars are behaving in the right way. So literally, the people that are regulating bus routes in the United States are much more advanced on the matter of algorithms than effectively the biggest, or one of the biggest, financial or sort of industries in the world. So they have much better understanding of how algorithms behave than the SEC and CFTC, etc. Although they are getting there. So to answer your question, one is, I think a lot of the kind of the nature behind what it is they're regulating is very much consistent with what Jim has been talking about in terms of the separation of things. And number one. Number two, with these breakthroughs, there are certain standards that can be imposed on testing that just were not there, years ago. And I think they will go a long way to make sure that people are much more rigorous in testing.
Okay, thank you. Do you have any questions now? I suspect everyone is already started.
And besides that, there's a bunch of formal methods people that have been well trained in the UK. They're looking for work probably. So think of them.
Well, still, so I understand a lot value in model. Oh, cool.
Yes, just a quick question or sort of observation. Actually, I thought that was very good from Denis, and there's great value, I think, in the types of technique you're applying for testing precisely that, matching engines, dark pools, single systems that you're in control of. Now, I know this is a debate we had last year. When you've got an ecosystem that's non-linear, there are provable problems in the sense of the way nonlinearity acts in terms of sensitive dependence on initial conditions that make this very difficult. It make the formal verification actually prove it. I think it would be provable that in a combination of the systems it could not work. So just a little care is needed. But I do think it has great value within single systems, precisely that, matching engines, dark pools, that sort of thing, where you're testing a single engine with people coming in, where you've got that engine and the rules in that engine makes complete sense.
Sorry, I didn't mean to. Please continue. I didn't mean to interrupt.
Sorry, did you?
I felt like I wanted to comment on that.
Yeah.
And I remember the conversation you and I had. I think about a year ago. Different venue, but just as intriguing as interesting. But I wanted to allow you to finish before I could comment.
Sure.
On
Well, go ahead.
Okay, perfect. So I think a couple of things. So first of all, so absolutely, agree with you that when it comes to, as you mentioned, single kind of system scenarios and being able to test them, it's okay, that's great. So I think you and I both agree on the value of applying these techniques to those types of scenarios. Something that I think is a natural lead from that is when you have a matching engine, and so let's say you have some sort of specification that you make available to your clients and to regulators, is if you go from effectively describing that using English prose to something that's machine readable, i.e. using something like fixed orchestra, then you get into the state where the person that's actually connecting to it can be much more rigorous in terms of how they're testing their systems against that and how they're demonstrating compliance to regulators. So now you have the scenario where the person has to test their systems when it's trading against the venue, becomes much, that process becomes much more rigorous and saves people a lot of time and money to that. I think taking that step and then going to kind of infinity and thinking and asking a question like, okay, can formal verification prevent things like flash crashes? Or these scenarios where you have thousands of trading systems, they're all interacting with one another. How do you reason about all of these different interactions between many, many different systems? For that, we have to distinguish between two things. First is this notion of, let's just assume that we verify that all of them can make sure they will never send out an erroneous market order or something else like this because of a glitch. So they're all are implementing correctly the economic decisions that they were designed to do. Next question is, we have two types of scenarios. Number one, we have a question of market design, i.e. if a market can drop 20% over 3 hours, there are no, let's say, circuit breakers designed for that. Is that a question for testing and reliability, or is that a question more for economists and thinking about what is a proper market design that facilitates, exchange of goods, etc. But also, just to kind of advocate, use formal verification for that. NASA is working on something called next-gen aircraft systems, where they have a similar scenario where they have to think about how autopilots will negotiate with one another in terms of who's going to take off, who's going to land. So if you think about flight industry, let's say 10 or 15 years from now, there's going to be a lot more aircraft in the sky with the same amount of sky. So how do you make sure that you can actually much more efficient in terms of utilizing the airspace? And something that people are trying to do is they're trying to minimize the number of air traffic controllers that we have on the ground. And a way to do that is by having autopilot systems inside those jets actually navigate with one another and make sure that they can actually do that in a safe way. So next-gen aircraft systems is a project with NASA that's working towards that goal. And they're obviously using formal verification to make sure that the algorithms that are encoded within the autopilot system can actually safely navigate or negotiate with one another, make sure that you don't have 10 aircraft that are all just crashing to one another over Heathrow. So formal verification is, it's the science of algorithms. And anytime we're designing algorithms, we should probably try to use that. Hopefully that answers.
No, that's very interesting, and I think that's better argued than last year.
Every single day it says, I'm better now than I was an hour ago. So.
If you are talking about a highly regulated industry like aircraft, where you're not going to produce the autopilot system in aircraft, the amount of testing that's gone through, the amount of regulation that's under, and the fact that there's health and safety rules which people abide by, the algorithm industry will never be like that. There will always be algorithms going in that have been better tested, but not anything like that. And also the nonlinearity and the speed of the speed of the process means that we can end up, if we put little bits of latency in the system, we can create very anomalous conditions very quickly that rapidly proliferate in a way that becomes very difficult to test. You're multiplying out the sensitive dependence on initial conditions, basically. It becomes a multi, I don't like to use the word chaos, but let's just call it sensitive dependence on initial conditions. But the fluctuations become macroscopic very fast, and that's there's very little that can be done about that. That's just the nature of nonlinear dynamics. So if you had control, if you could say step the system so you could control it to once every second, you could probably avoid most of those. When you've got a system that's running in microseconds, you've got a real problem. These things can vary rapidly. And inaccuracy, when we run these systems with exactly the same techniques, exactly the same algorithms running in them, you can get very, very different results just because of a 1 microsecond difference in the way something hit the engine.
Yeah, I think it's important. Yeah, just to follow up on the summaries, I think it was one of the earlier presentations. I don't know if it was Iosif or one of the other leaders of Extent, is that always expanding your toolkit of testing tools and integrating and pulling them together. Model-based testing is another very valuable tool. Some of the techniques and infrastructure that Nick's company has is another part of that tool, and I concur with him. When you start moving into the very stochastic world of nonlinear dynamics, that requires a different level of testing and structure, and that that model-based testing is really specific when you can do an algorithm or a protocol. So to Iosif's point, it's not applicable everywhere, but where it's applicable, it's very applicable, and very important, I think, that to use it. So in those places, if it were my money, I would be using some of the stuff from all 3 of these or 4 of these approaches actually to ensure, using some of the stuff from Nick, using some of the model-based stuff to put together the whole the entire solution and approach. And I also want to make sure that people understand that you can validate. And someone else talked. I think the gentleman from the Moscow Exchange talked about this the best earlier today, and that's that you can get a perfectly running system. And if it's not designed for test and it's not designed for resiliency and failover, people pulling network plugs and you losing solid state disks in the middle of the day and things like that. Those are another level of engineering where chaos engineering can help you. They took a better approach where they're using a management approach where they manage their hardware. I I hope he does realize that when I worked in the aerospace industry there's a certain level of defects of new products. So just going through a process where every 3 years we're going to replace with new products does not eliminate the failure, because a certain number of the new products are already defective. So your process by saying, oh, that part's life limited, we're going to take out the old part and put in a new part, actually what can happen is you've just injected a fault because that new part may be faulty. So that's another, these are all kinds of, the bottom line is systems engineering is very difficult, and almost every aspect of system engineering actually touches on some societal risk, including human life risk. If you think about where Internet of Things, where we're going in terms of this technology and how it's interacting with us. So.
Thank you. Rajan, do you have anything to add?
Firstly, just to expand on something Denis said, next generation of air traffic control will be satellite-based to cope with the projected increases in air traffic. Traditional ground-based radar simply doesn't have the capacity to deal with the projected increases in air traffic control. In our industry, we use a multitude of techniques. It's not simply, one technique will solve all our testing and simulation and verification requirements. It's a multi-pronged attack to prove to ourselves and to our clients that our software and our hardware will meet their reliability needs. Okay, we simulate at many different levels. We test at many different levels, from a component level to a complete spacecraft level. It's a multi-pronged attack to ensure what we launch will work. And if there are failures, the subsystems are architected in a way that failures will happen gracefully. So, for example, we might use techniques such as, let's say, redundancy. So it's all about reliability and continuous availability of services within my industry.
Thank you. And we have a minute for the last statement. Milan, would you like to say anything?
1 minute?
Yes.
So like closing remarks, you mean? Something like that.
Yes.
Thank you for the honor. Well, I was actually thinking about that. It seems that trading systems are getting ever faster and need to process more and more data. So obviously new challenges arise. Like we get better hardware, we get faster CPUs, we get much larger FPGAs, but that creates problems for people responsible for testing, because the larger application, the more data you process, the more likely you are to run into some issues either with performance and functionality and so on. So I think testing is going to be and quality assurance very important in the upcoming years. And I think conferences like this is good to bring people together and exchange ideas, and even look into opportunities how to cooperate, because it was mentioned before that you want to avoid repetitive tasks like automate. That means don't reinvent the wheel. I think it can be applied to the industry scale as well. There are multiple companies who are all dealing with the same problems. If we cooperate and use just one solution, we can focus on the added value and on more useful things. So
Thank you very much. And now formal world of avionics will meet with fragile web development world, and we will use our Twitter wall out there to define who will get the drone. And I would like to say thank you very much to all of you indeed for spending the day with us. It is very much appreciated. I hope to see some of you next year. Thank you. And